Cauchy's theorem. It is an important theorem in algebra. It says that let P be a prime. Let G be a finite group. It is important that G is a finite group, and let P divides cardinality of G. Then G has an element of order P and consequently a subgroup of order P. If we prove that G has an element of order P, then consequently this happens, because suppose if A is an element of order P, then we can say that cyclic group generated by A has an order P. So the cyclic group generated by A will be a subgroup of G, since A is an element of G. We have taken like this: A is an element of G which has order P. So to prove this theorem, we are taking a set X of P tuples in such a way that this P tuples G1, G2, if we are taking that X as set of all P1, P2, etc. G1, G2, etc. Gp, such that their product is equal to identity. That is, we are taking X as the set of all P tuples G1, G1, G2, etc. Gp, such that Gi element of G, for I equal to 1 to etc. P, this Gi's are coming from our group G, and G1, G2, etc. Gp, that is, their product is equal to the identity element E in G, in such a way that we are taking a set X. Now we claim that our P, we have taken a prime P, and P divides cardinality of G. This is given in our theorem. P divides cardinality of G. So now next we claim that P divides cardinality of X. How we can prove this P divides cardinality of X? For that, so we are forming this. In X we have P tuples, isn't it? X we have P tuples. It is a set of P tuples. So we are taking a G1, G2, etc. Gp minus 1 we are choosing randomly, but we are choosing Gp in such a way that this G1, etc. Gp minus 1, their product whole inverse would give you Gp. Then only we get this G1, G2, etc. Gp equal to the identity. So we are forming such a group X. So we can choose G1, G2, etc. Gp minus 1 in a random way, but to choose Gp, we need this G1, G2, etc. Gp minus 1 whole inverse. It should be Gp. Then only we get the product as the identity. So Gp is determined by this G1, G2, etc. Gp minus 1. This can be any element of G. So we can say that Gi has cardinality of G choices. Each Gi, this G1 be any element of G we can take. So each Gi has a cardinality of G choices. That is, we can say that cardinality of X is equal to cardinality of G power P minus 1. Because why? This Gp is determined by all this Gp minus 1, and each Ga has a cardinality of G choices. Our cardinality of G power P minus 1 will be cardinality of X. Okay. We have given that P divides cardinality of G in the theorem. P divides cardinality of G. So here we got a cardinality of X is cardinality of G power P minus 1. So clearly P divides cardinality of X. P divides cardinality of X. So our claim is true. P divides cardinality of X. Now we are taking a cycle sigma. A cycle sigma 1, 2. Sigma is actually a cycle 1, 2, 3, etc. P in SP. What do you mean by SP? SP is the what we can say, it is the permutation group. Okay, so sigma is a cycle 1 2 3 etc. P in SP, and we are letting this sigma to act on X. So X is G1 G2 etc. X is the set of all P tuples G1 G2 etc. GP. So we are letting sigma to act on this G1 G2 etc. GP. So what we will get, we know that sigma of sigma into X, that is equal to sigma of X. It is acting like that in SP, isn't it? So we will get G sigma of 1, G sigma of 2 etc. G sigma of P. We will get like this. What is sigma of 1? Sigma of 1 is mapped to 2 here. 2 is to 2 goes to 3. 3 goes to 4. And hence it is going like this. So we get, when we add sigma to this X, we will get G2, G3, etc. G1. Sorry, G1, G2, G3, etc. GP minus 1, GP, G1. Because here we get the last element here is G sigma of P. Sigma of P is mapping to 1. This is a cycle, isn't it? So we get G of 1 here. So we when we let the sigma to act on X, we got the elements like G2, G3, etc. G1. Clearly this is an element of X. Why? Because when we consider its product, it will always equal to E, because G1, G2, etc. GP is E. So here also the product of element is E. So it is clearly an element of X. So what we can say, when we act sigma on X, we got an element in X. So we can say that X is an sigma set. We can say SP set. We can say G set. X is an G set. Similarly, here is an SP set. We can say. So now consider the subgroup of SP, cycle by sigma. Because if sigma is an element of SP, cycle by sigma will be a subgroup of SP. It is clear. So similarly, as sigma act on S, the cycle by sigma will act on X. We are letting this cycle by sigma to act on X by iteration in a natural way. Now, what is the order of cycle by sigma? Order of cycle by sigma, it will be equal to P. It is clear because sigma is a cycle. Sigma is 1, 2, 3, etc. P. So cycle by sigma is of order P. It is clear. And it is important to note one theorem here. That is, we have a theorem. We have to apply one theorem here. That is, the theorem says, let G be a group of order P power n, and let X be a finite G set. X is a G set. It is a finite G set because G is a group of order P power n. Then cardinality of X will be congruent to cardinality of Xg mod P. This we have a theorem. Actually, we can prove it easily. So using this, we are using this theorem here. So here the order of cycle by sigma is P. So using this theorem, and we can say that the cycle by sigma, when we act on X, X is a cycle by sigma set. So cardinality of cycle by sigma is P. So we can say that it is a power of P. P power 1 is P. So we can apply this theorem. So using this theorem, I can write cardinality of X is congruent to cardinality of X cycle by sigma mod P. Okay, I can write like this. Now we had a claim that P divides cardinality of X. We have proven that P divides cardinality of X. So, and here we got a congruence like cardinality of x is congruent to cardinality of x cycled by sigma mod p. So, we must have p divides cardinality of x cycled by sigma. So, now we want to find what is x suffix sigma, because in x cycle by sigma we have to find which elements are fixed when we apply cycle by sigma on x, which all elements are fixed, that we want to know. So in that case we know that when we consider only sigma, when we apply to G1, G2, etc. Gp, we get G2, etc. Gp, G1. Okay, this we get. So sigma fixes this G1, G2, etc. Gp. It is equal to G1, G2, etc. Gp if and only if G1, G2, etc. Gp, if and only if G1 equal to G2 equal to etc. equal to Gp. Then only we get this sigma fixes this G1, G2, etc. Gp. Otherwise we will get a next the coordinates are get changed. So sigma fixes this G1, G2, etc. Gp if and only if they are equal. So what we can say? We can say cycle by sigma also fixes this G1, G2, etc. Gp if and only if G1 equal to G2 equal to etc. equal to Gp. Now, so this we have taken. So x by cycle sigma, it must one, we know this one element, at least one element, e, the identity element e, because it is all the same, and x cycle by sigma has at least this element. This we know, and we have already said that p divides cardinality of x by cycle by sigma. See, we only know one element e in x cycle by sigma. So p divides cardinality of x by p divides cardinality of this x by x cycle by sigma. So there must exist an element a in G such that a etc. A is an element of x cycle by sigma. Okay, it must be, there must be an element of G such that it is an element of x cycle by sigma. That is, when we apply sigma, it fixes. Okay, hence what we can say, a power p. It is p times we are taking. Yeah, this is taking p times. So we can say a power p is equal to the identity e, which implies that cardinality of a is equal to p. Okay, so a has an order p. Thus we have proven that there is an element a in G which has of order p. Then we can consequently we get the cyclic group generated by a is of order p. So we have proven the Cauchy's theorem. Hope you understood. Thank you.